Flow velocity upstream and downstream of a hydraulic jump. Understanding the flow velocity upstream and downstream of a hydraulic jump is crucial for civil engineering applications, particularly in the design of hydraulic structures. A hydraulic jump occurs when high-velocity flow transitions to a slower-moving body of water, resulting in a sudden change in flow characteristics. This study majorly focuses into the concepts of upstream water depth and downstream water depth. What is a hydraulic jump? A hydraulic jump is a phenomenon that typically occurs in open channel flow when the flow transitions from supercritical to subcritical conditions. This transition can be observed in rivers, spillways, and other hydraulic structures. The jump dissipates energy, which is essential for preventing erosion and ensuring the stability of channels. Key parameters of hydraulic jumps. Upstream water depth. This is the depth of the water before it encounters the hydraulic jump. It influences the flow velocity upstream. Downstream water depth. The downstream water depth is the depth of the water after the hydraulic jump. This depth is typically greater than the upstream depth due to the energy dissipation that occurs during the jump. Flow velocity upstream. The velocity of water before the jump. Flow velocity downstream. The velocity of water after the jump. Calculating flow velocities and water depths. To analyze the flow characteristics before and after a hydraulic jump, we can use the following equations derived from the principles of conservation of momentum and energy. Energy equation. The energy equation for a hydraulic jump can be expressed as where V1 equals flow velocity upstream, V2 equals flow velocity downstream, HF equals head loss due to the jump, G equals acceleration due to gravity. Momentum equation. The momentum equation for the hydraulic jump can be expressed as Q equals A1V1 equals A2V2, where Q equals flow rate, M superscript 3s. A 1 equals cross-sectional area upstream. A 2 equals cross-sectional area downstream. Example calculation. Let's consider a scenario where upstream water depth, H1, is equal to 2 m. Downstream water depth, H2, is equal to 4 m. The flow rate, Q equals 10 m3s. Step 1. Calculate upstream velocity. The cross-sectional area upstream can be calculated as follows yen. Step 2. Calculate downstream velocity. The cross-sectional area downstream can be calculated similarly. Significance of understanding flow velocities. Understanding flow velocity upstream and downstream of a hydraulic jump is essential for various civil engineering applications, including designing spillways, ensuring that structures can handle sudden changes in flow. Preventing erosion, managing energy dissipation to avoid channel erosion. Flood management, predicting flow behavior during flood events to minimize risks. In conclusion, the flow velocity upstream and downstream of a hydraulic jump, along with the corresponding water depths, play a significant role in hydraulic engineering. By mastering these concepts and calculations, civil engineers can design more effective and safer hydraulic systems. For further reading, you may explore the following scholarly sources. Hydraulic jump analysis. Open channel flow.